Hello, everyone. Welcome to another binary episode of the Day Zero podcast. I'm Spectre, with me is Z. As always, I'll let Z get into the spot the Vuln here, and then we'll get into our topics.
All right. This week's Spot the Vuln is not coming up in chat. There we go. This week's Spot the Vuln is a JavaScript issue. Core idea of this code is kind of simulating you've got some random window, some web application. It adds a event listener for message, so sending like a post message across the frame or whatever. You can send it a message, it reads a response target from it, checks that against the whitelist, and then get some sensitive data. Assuming it passes the whitelist check, it'll get some sensitive data, whatever that might be, and send a post message back up to the parent using whatever, using the value that supposedly passed the whitelist check as the target for the post message. So getting into it, core problem, there's kind of a couple things going on here. In terms of what might look suspicious to you, one is just the way it's doing the validation of get host. Someone mentioned in chat, they thought it looked suspicious and there should be a better way of doing that. So the way I'm doing get host here, for those listening, function get host takes in a URL, creates a anchor element, sets the href for that anchor element to whatever the URL is, and then returns the host of the anchor element. I have seen this code pattern a number of times. I'm not exactly sure why it's used. Creating a new URL object is a safer bet here, and won't do the same kind of default actions that an anchor take. So the problem with using the anchor take here is when you get a URL that like doesn't have a domain or something in it, or kind of like malformed or something, it's going to think it's a relative link. Is what if you provide it as the href for like an anchor tag? So it thinks it's relative, which means it's going to have whatever domain you're currently on when it comes through. So the other thing that can look suspicious is the fact that the whitelist goes through this get host target, whereas the call out for the post message, the target for the post message, uses kind of the original value. So kind of seeing that, not necessarily a double parsing of the value, but the fact that you have a different value being checked versus the one that's actually used should look suspicious also. So in this case, you can kind of take advantage of that bad get host thing. If you send it in just the asterisk or star character, which is treated as the wildcard in the post message, you send it in that as the response target. It'll go through into get host. Get host is actually going to think, oh, this is a relative URL, and it's going to give you the host of the current page, which is going to be in the allowed list. It is UR allowed tags from the same domain. So basically it'll pass there, and then it uses the star when it gets down into the post message again. So even if it were to, for this case at least, use the get host and just use that value in the post message, you wouldn't have had an issue anymore here. But the fact that it kind of parses it and then doesn't use the response there lets this issue happen. Passing in the stars one way. There was also another solution that feels a little bit more complicated. It is passing in a sort of malformed URL. I didn't think about this one. Somebody else actually, a few people solved it in this way. So that would be using something like, I'm just typing it into the search box on Imager here, but using something like https : not / the attacker's domain. And what ends up happening with this is in get host, it's going to see this as, so this case with HTTPS, if you're on an HTTPS page, it'll see that as a relative URL. If it's on an HTTP page, you'll need to change that to HTTP : I'm not sure if there's some history behind this notation. I meant to kind of look into that. But ultimately, as long as the protocols match, it'll treat it as a relative URL, so this host match will pass. And then when post message gets it, it just pulls the domain out of it and uses that. So again, passes it. There's some weird stuff going on with that one that I'm not exactly sure why. I feel like there's probably some traditional reason for why that The protocol matching aspect happens with the anchor tags. There's probably something in the spec about parsing it for post message and how it parses the target there, but uh, I don't know. It is a little bit weird, but it does work. So at least keep that in mind. I'm not sure. Yeah, honestly, it's a great solution. I can't completely explain how that one works though. Using the wildcard makes sense. The host becomes relative, so you get the domain check passing, and wildcard obviously has a meaning, but yeah, that's another really good solution.
As far as the core issue goes, I'm sure some people who tuned into yesterday's episode probably have a bit of deja vu with that. It's a pretty similar root cause, but yeah, and that second solution is pretty cool. I never even I didn't even know that was really a thing. So yeah, it's we or I at least learned something from that one.
Yeah, so did I.
All right, so we'll get into our first topic here, which is a post by Google security blog. They did a year in review of 2022 for their VRP or Vuln research program, which we've shouted out a few times before because their rewards and stuff are pretty good and they have some pretty interesting targets. So yeah, I just thought we'd bring it up. Have an opportunity to talk a little bit about the VRP. Mostly, what they do here is they shout out some of their top researchers. I think they say there's a few researchers here who had like over 200 reports last year,
Yeah, the
which is pretty insane. It's almost like hard to comprehend that many, but
yeah,
yeah,
the one guy here, Amon Pandy of Bugsmear, actually checked them out a little bit. It looks like they might have been reporting several sort of side channel type issues. I don't know for sure. I didn't actually get to track down exactly what they reported, but they have this little testimonial section on their page that doesn't seem to be loading right now. Uh, where they have one from someone at Google mentioning, like, yeah, here we go. We're curious to know how you're finding these types of bugs since we'd like to close out all of these side channels. So it sounds like they've got some sort of, in a sense, like a secret sauce that they've been hunting for, which is awesome. Uh, but yeah, and that is quite a few bugs to report. I mean, 500 across or since 2019 also.
yeah. So yeah, a lot of the stuff they showed out here is around their Android and Chrome VRP, which makes sense. That is Google's like high value targets. That is like their major product lines, and that's where they put a lot of their security focus. So yeah, just a bit of a shout out, I guess, to the Google VRP. It is worth checking out if you're looking for something to do. It is one of the more well paying programs. It might not pay super high, but as far as like Vuln research programs go, it's pretty decent. So, um, yeah, just wanted to give that a quick shout out. There's
Yeah,
also
like
something else that they talk about near the end that I wanted to bring up, and that is they're they're opening up their Bug Hunter University or BHU. I don't remember seeing this before. I don't know if this is something that's been there for a while but was kind of closed off, or if it's newer. I'm not sure. I do want to check it out though.
it's
So
been there for a while, like, and it's been
okay,
accessible, like, because this is just like their bug hunters, effectively just their playlist of some bug issues. Like
okay.
that's I'm
I
not
don't remember us
sure. So,
talking about it before, so I did want to give it a quick shout out, but
I
perhaps
think
I just
it,
forgot.
yeah, I think it's like pre-existed the podcast.
But fair
Um,
enough.
like they do mention that in 2022 they've made the learning opportunities available there some are more diverse and accessible. So maybe it's just adding to their articles, adding more to it. Um, and I know they had that is it hacking Google? Yeah, they mentioned it here. They had that playlist and that stuff coming out. Just I guess it was late last year, but
Yeah. Overall, it's nice to see how open Google is with security research, especially when you consider like the big corporations. I think there's no argument to be made that like anyone can test Google on how open they are with sharing stuff from their program and some of the stuff that's happening with their products. So yeah, there's some cool information there. It might be worth checking out.
I feel like
But
Microsoft is fairly open. I think Microsoft has a bit less of a surface because they just have like their binary stuff, Windows kernel, Hyper-V. They don't have the same sort of presence that Google has also across the web. And for like all of their web issues that we see also with Google. Um, but Microsoft has felt fairly open, at least in terms of having the reports, disclosing them, doing their own research. May not be Project Zero, but like they've got their own stuff coming out there too, like the browser VR team and stuff.
they have some stuff, but I think that's mostly been over the last year or two. It's a lot more recent. Whereas Google's been kind of on this grind for a while with putting out this stuff. So yeah, some good resources, and like I said, it's worth checking out their VRP.
We'll say
Uh,
one thing that slightly bugged me about this post, and
yep.
this is not all that important, but their chart. You'll
Oh,
notice
no
from
y-axis. Is that what you're gonna
not
say?
even not even not the lack of it, but the fact that you have this growth of 2 million here, and it is exactly the same as this 3 million or 3.3 million growth. I just feel
The
like the
scale is
distinction should
weird.
be bigger. The scale seems a little bit off, especially given the 3 million growth there is kind of much more obvious. That said, it's a random chart. It really doesn't matter.
I will say this definitely wouldn't be appreciated on like the data is beautiful subreddit. It's, it's a bit lacking as far as charts go, but it does convey like I guess what they're trying to say with the rewards over time. So, and yeah, like $12 million in rewards in 2022 is pretty impressive. So yeah, all
And
right. So
highest,
well,
actually, I just noticed their highest reward was 605,000,
yeah, good shout. I wonder
which,
what that must have been like a pretty insane chain.
yeah, they only mentioned finding yet another critical exploit chain. GZOBQQ submitted our highest valued exploit, which I assume then would be this highest reward,
Yeah.
but no details on it. And not even a Twitter link or something for the person to see if there's any write up.
Yeah, it's interesting though, because yeah, like I don't remember the last time I saw a reward even like a quarter of that high from uh like that was posted. So I'd be curious what that chain is. But like you said, unfortunately, there's not really many technical details in the post. It's just more of like a thank you to people. So yeah. All right, so we'll get into some of our vulnerabilities for the episode. Up first, we have a post from GitHub Security Blog on a vulnerability in Adreno or KGSL for Android devices. So now we're able to kind of continue on that Google thought line. And this was basically an info leak, but that kind of downplays it as it could actually allow you to leak like large amounts of data, including from other processes. And it was sort of found by accident. So the post covers a lot of background on the GPU and what it does. What's important as far as the background goes is the fact that you can map shared memory between the GPU and the CPU and use that to pass buffers that contain things like commands or input data or whatever. Ultimately, shaders and whatnot resolve down to these command packets, which get processed by the GPU in these indirect buffers. And there's some protections in place to make sure that you can't use privileged commands as a regular user space application and whatnot. So yeah, as like part of investigating into this and trying to understand it a bit more, uh, he wrote up some code to basically do a pretty simple task. Like it would set up a command buffer and a destination buffer, set up some write packets and send it off to the GPU. But it wouldn't like wait before it would send it off after writing, which is a little bit important, and I'll get into that in a little bit. And what he noticed was sometimes when this code ran, it didn't. The command buffer wasn't parsed properly. So like what it was supposed to do normally was it was supposed to write tagged hex 41 data into the destination buffer, but sometimes it would fail. And not only was hex 41 not written, but errors were dumped into the kernel log about opcode error interrupts, dumping the opcode as like this hex 7e code, which he'd never put in the command buffer in the first place. So that kind of, set some alarm bells off that something was going wrong. Debugging this was pretty tricky because he noticed there was some kind of timing angle to it. As if you wrote the commands delayed for a bit and then sent them after the delay, it would work. Um, but there's no real way to read data from the GPU using command packets. And even if there was, that command buffer isn't super reliable. But what he hypothesized here was that the GPU was getting an inconsistent view of the buffer compared to the CPU, which he ultimately suspects comes down to a cache coherency issue. So when you write data through the CPU, of course, that data is going to be updated in the CPU cache. But what's maybe not so obvious is that it that cache contents that gets updated won't make its way to physical memory right away. That only happens when the cache gets flushed. Now, while all the CPU cores are coherent with themselves, so like one CPU core will see the same data as another CPU core, they're not necessarily coherent with things like the GPU, for example, or any other like external devices. And this is a pretty subtle bug because when they dive into the code, he mentions that the map user mem ioctl actually calls get user pages on the command buffer. And for those not familiar with the kernel interface, get user pages, um, it's kind of used to grab a reference to the page so that like the user can't free it from underneath you or whatever. And it also calls like flush related routines to flush the cache. So it looks like there shouldn't be any cache coherency problems because the data should be getting updated on the physical pages. The problem is ARC64's like architecture code for handling the flush anonymous pages request is a NOP. It's just an empty function. It doesn't do anything. So it's sort of like lying with the ARC64 architecture. The way this was exploited was pretty cool, and it basically involved laying the command buffer across two pages. So by having one page contain the opcode for the write command, which is reliable, and then having the values that get written bleed into the next page, they can basically have the first page be cache coherent and have the second one not be, and thus leak data by sending GPU write commands and having like unreliable data getting written to that destination buffer. So it's a really cool vulnerability. Leaking kernel memory is a lot trickier than leaking like user space process memory, because the kernel has its own page allocator, and generally like they'll stick to their own zones, and it won't be easy to leak. Because ultimately, like the data that's being leaked is coming from what's supposed to be user pages. I won't go too much into this because it's going super specific into the Linux kernel page allocator stuff. But basically, what they use there is they target a special type of page that's mapped to user space, but also with this like high user flag. And like this page also can't be mapped via remap PFN range, as it can't be sent as it can't be set as a PFN map or an IO page. What they used there was the asynchronous IO or AIOSys calls, which would indirectly create high user pages for the ring buffers. Though they even had to do some additional trickery to get that mapped because the GPU tries to set up the memory region as a DMA buff. So when it when it looks up the page that's mapped for the AIO, and it sees that it's not an anonymous page and it's not mapped to a DMA file, it'll fail. Interestingly, though, it only performs that check on the first VMA in the region. So again, sort of similar to the previous trick, by doing two separate but adjacent user space mappings, you can map the both of them in and kind of slip the second one through. So yeah, I mean, it's a pretty insane exploit chain. And as always, there's a lot of like good background info from these posts, and I think it's pretty accessible, even if you're not super into the low level like memory specifics of how caching works and whatnot. I think it does do a pretty good job explaining what's going on. Um, as to how exactly like all the specifics of the cache coherency stuff, it's not really talked about in the post, but it's also not super relevant. Mostly what's relevant is the fact that it happens. So yeah, I mean, it's a pretty crazy bug, and it can allow you to leak both kernel and user space data from other processes. So it's an extremely powerful exploit primitive, despite the fact that it's like a read. It doesn't give you corruption, but it does give you a lot as an attacker. So
I do
it's a
wonder
pretty unique scenario.
if you could use it in more of a corruption way. Like, I don't know. So you need some way of like better grooming what it's going to use. But if you could corrupt the command buffer, like have it start reading into that page the non-coherent page, and have that actually filled with data you wanted. Like, I don't know, I could see maybe some sort of exploit there, but I don't know how you'd get to that point. And I think they kind of reference here. Um, there's just kind of a throwaway line somewhere in the middle here where they talk about like there's no way to do that basically, but it feels like the sort of bug that like there could maybe be some other creative exploits on it if you were spending a lot of time. In terms of categorizing the bug, I was thinking about like it's hard to categorize like what the issue is here. Like obviously the issue is clear in terms of what the bug is and what it does, but at the same time, it's a function that's a no op, just not implemented functionality basically. Like it's a weird vulnerability or weird bug class in that sense.
It's not really obvious how you would patch it, is how I'd say it. Yeah. Um,
Well, patch it really just comes down to whether or not they have support for doing it at the hardware level, but um,
yeah.
I assume there is a way to do so. It is kind of lower level than my knowledge, I guess.
Yeah. Um, Ultimately, though, like I said, it's a pretty cool bug. It deals with something that a lot of people don't want to think about and just kind of stick away in a black box. Like nobody really wants to deal with like cache coherency problems. It's something you want to wave off to like the hardware or whatever, typically. But in situations like this, especially when you're dealing with a GPU, it is a major problem, and especially because with the GPU, where performance is top priority, that's why the GPU is exposed to user space like it is, because you need like that low latency access. Caching becomes very important, and it's very heavily leveraged uh, with how like commands and all these things are ran. So it's a problem that you can't really avoid. You have to deal with it. And as pointed out by this blog post, it's not an easy problem to deal with by a long shot. So yeah. Really nice post. I enjoyed this one a lot. It is a little bit long, but that's because it goes into a lot of the background detail and is what makes it accessible to people not familiar with the area. So
Yeah,
yeah.
definitely a cool finding.
And just a funny thing from chat, IPR mentioned I always spell ioctl out. I never heard it pronounced ioctl. Yeah, I've heard it said like IO control, IOCTL. I just find ioctl a lot easier to say, so that's why I say it like that. But yeah.
Yeah, I tend to say it the same way. It flows a little bit easier just to say ioctl.
Yeah. All right. We do have another topic that kind of touches on Android as well, and is also a kernel bug. Z, do you want to get into this one?
Yeah, I can. This one is a much simpler bug. In fact, the actual vulnerability here, I believe they have the source code. Yeah, right here. Uh, you've got the call in on this driver and a copy from user that goes nicely into this write buff. Has or this is on the stack, has a maximum size, has the copy from users. This is user data. It's just copying whatever the user sends, however long it is. User controls how long. It's just a straightforward Stack Overflow in the kernel for this device driver. It really is nothing more complex than that. What I like though about this post is actually talking about the fuzzing method and how they found the bug was using, as the title goes, the world's worst fuzzer. Actively, they iterated all of the files on the device um, and just wrote garbage to them. Write garbage to the file and see what happens. And they got a crash within a handful of seconds. So really dumb fuzzer, really simple vulnerability. I don't know. I like the fuzzing technique. I mean, it's not an elegant technique. It's unlikely to turn up some really deep bugs. But it reminds me of that meme. I mean, sometimes you just get the crashes doing stupid things. Piping dev random into a program.
Yeah, it was kind of funny because even though this fuzzing was so dumb, it was so effective that they had to tune it back a little bit too. Because as soon as they ran it, they got like a crash within 1 second. So they basically had to make the fuzzer not do any reads, because it would actually try to do both reading and writing. So they removed like the read stuff, and they also like reduced the number of threads and whatnot. So like it was more readable, and they were able to parse through it better. But yeah, the interface is also yeah, I do love that meme. The interface is also a little bit interesting because this is ultimately hittable through procfs, um, which you don't really see too often compared to like your typical, character device. Open it up, issue a bad ioctl, and on you go. Yeah, it's a bit of a it's an area you don't really see quite as often, but the vulnerability is pretty straightforward. Exploitation, I would be curious on. He doesn't call out stat canaries or anything like that. I think he just kind of hand waves off as like this could be exploitable depending on the mitigations in play. Typically, like a function like this will be instrumented with stack canaries, so probably you couldn't exploit this on its own. That said, I've never owned like a FiiO M6 or whatever. I think it's not quite a phone, but it's supposed to be like a audio hi-fi thing. Um, so like that's why it has its own touchscreen drivers and stuff. It's kind of using like an Android base, but it's also got its own software stack. So yeah, like it's possible it doesn't build with canaries, but I think it more likely it does. Which in that case, exploiting this would be more difficult. But ultimately, what the post wanted to talk about more so is just the vulnerability and how they found it with the dumb fuzzing, which I think that was kind of based on Gamozo Labs work, because he did a stream a while back on like Android VR, on like some older device, and I think that's where the world's worst fuzzer terminology came from also. But yeah, not a super crazy bug or anything like that, but it is fun to see vulnerabilities come out of such such easy and straightforward fuzzing.
Yeah,
You know.
vulnerability, honestly, it just isn't that interesting. The fuzzing gain, it's simple, but it worked. Of For those of you who heard kind of Spectre laugh at the meme, I pulled up kind of this older meme about writing like a vulnerability scanner that does whatever complex thing, and then someone else writes the dumb fuzzer and finds several vulns with it. I mean, sometimes you just need to get moving and do something, and bugs will shake out. And other times it's more complicated. So, I probably wouldn't expect to do this and like find uh very many useful maybe on Android, like on a mainline Android device. Probably going to have a little bit less impact.
Yeah,
Uh
it's kind of tailored to the target a little bit. Like because it's a lesser used device with a custom driver stack that has like these low hanging fruit bugs, that's why it's so effective here. Yeah, I wouldn't count on this being as effective on a main line, like a flagship phone or something.
yeah,
It's just
but I feel
not
like
gonna happen.
it's still worth keeping in mind because not everybody's fuzzing the hard end targets. I mean, there's a lot of software out there. A lot of it is more like this, just not much hardening done. Just code that's
Yeah.
pushed out to do a job. Nobody's thinking about security.
Yeah, you could take this into like the IoT space and probably have a lot of
Yeah.
fun. So, yeah. All right. But yeah, not too many topics this week. We just had a few very interesting ones. So that's where we're gonna wrap up the show. Z, unless you have any last minute thoughts, we'll wrap it up here.
Yeah, no shout outs this week.
All right, cool. So yeah, thanks everyone who tuned in. If you want to catch past episodes, you can find recent ones on Twitch and all of them on YouTube, Spotify, Apple Podcast, and more links on Anchor. If you want to join the community, join our Discord and follow us on Twitter. Links for those are down below or in the chat as well. And with that said, we'll see you all next week.